the record button. And this week we're going to take a quick jog around Earth Sciences. We're going to talk about learnings from the course. And one of the things I'll do at this stage actually is turn off I'll hide our video.
Colin, this is Maxine again. We actually can't see you. We can only see the PowerPoint.
You can only see the PowerPoint? Yes, I've just turned off the audio panel.
Oh, okay.
Sorry, the video panel, because what happens is Zoom will record it with all of our faces on it. And that's probably not a good thing to do to you as tuning in, to have your faces in a little box in the corner of the video thing. So I've actually switched off the video. I've hidden the video panel so that it won't appear on the recording. So our voices will be there, but not our images, which I think is probably more appropriate for something that's going on the internet, on the web. So let's have a quick look at this week. The intention is basically to do a bit of a jog around the Earth Sciences, and then to have a look at the learnings in this week's topics, and right throughout the program, so we can start to hopefully draw some conclusions. So in this week we talk about what is Earth Science, and particularly we're looking at chapter 11 of Loxley, and I make a fairly critical comment at the start of the week in the Moodle that I don't think Loxley actually deals with Earth Science very well. I think Earth Science is a very productive field. And it really is one of those places where we can bring all of the productive pedagogies to work. And I think Loxley's a bit dated in what they offer. But again, in Loxley's defence, it is such a huge field, as we'll talk about tonight, that they can't really cover everything in 2 chapters. In the same way that this course, even though it's about Earth and space and biological sciences, we can't teach the content. The aim here is to point to it and to say, as a teacher, you will understand learning. And as someone who understands learning, you will understand how to direct people to learning in this area. And there are so many things I've taught in my career where I have not been an expert. But because of my teaching skills and my teaching framework and my aptitude, I have been able to apply those pedagogies and direct learners to the areas they need to go. And then at times you can be the sage on the bits that you do know, that is about learning and what we're going to explore. You can be the meddler in the middle. You can be the constructivist. And then you can be the guide on the side. You can be the problem solver in each of your classes and each of your roles. So the aim is not to suggest we need to be experts here. And so in defence of Loxley, all we need to know is how to teach this incredible science. It is incredible science. And this week we're looking at the different types of energy, and how energy changes and creates different energies. Heat creates different energies. Describe various sources of energies, compare and contrast, and finally look at this phenomenon we call global warming, because it's a much maligned concept. Is it real? Science says it's very real. And yet, because the nature of science, the contestability, the falsifiability, all these principles Popper put in place, the philosophy of science, means that global warming will be contested until the day that the planet can no longer cope. And unfortunately, that's our lot as humans. We're a very, very cerebral species. We are into democracy. We are into theory. We're into opinion. We're into testability and verifiability. Unfortunately, that's our lot. We are going to have to run with this and hopefully pick up some better science as we go through. So let's do a summary here, and we'll link it to the rest of the course too as we go through. We've asked what is biology. We've asked what is Earth, what is space science. Earth science can be broken down basically into 4 areas. Now, the reason why I'm presenting this is because really what I want you to do is understand that we can look at Earth science really from the science understanding perspective. We can teach geology, the study of the Earth. We can teach oceanography, the study of the ocean. We can teach meteorology, atmosphere and the processes and weather, astronomy, the study of the universe. All of these are discrete bodies of knowledge, and we can actually teach them, and we can teach them as science understandings, essentially. So the first strand is pretty much safe. We can look at the formation of the Earth, and we can see that most researchers can agree on certain hypotheses. Now, they are still hypotheses, because can they ultimately be proven? Well, we're getting more and more data, as we looked at last week, from the black holes, and from our discussion of the Big Bang. We're getting more and more data about the nebula hypothesis, about the solar system started from a microsecond, of massive energy, and the gases that emerge from that were hydrogen and helium. And then we see the nebula begins to contract. A flat disk shape, a proto-sun, the pre-sun at its centre. And so we're starting to see, these are all the things that we do agree on as scientists, and these are really teachable moments within the science framework. And I won't go through them again because really it's stuff that's come through the readings in the week. But really what we're talking about is the formation of the Earth as a planet. And if we can agree, and as we got there, 5 basic principles with a couple of subpoints, 5 subpoints, we can see that we've got our teachable science moments there. When we look at our scientific constructs, just excuse me at this point, I'm just going to just make sure I've got the right PowerPoint at this stage. And just minimize that and just check and make sure. I've opened the right version again. Okay, I have. I'm just wondering whether I've saved the previous. All right. I'll just go in here, File. Okay, that says it's the one. All right, we'll keep going with this one. I did notice I made some annotations to it that obviously haven't saved. But we look at the Earth's major spheres. We can talk about the hydrosphere and the ocean being the most prominent feature. We can talk about statistics. 71% of the Earth's surface, about 97% of the Earth's water. So only 3% of the Earth's water is fresh. So when we talk about pollution, we're giving students a context all the time. And we can talk about, the fresh water found in streams, lakes, glaciers, as well as that found underground. And of course, this brings into the melting and the rising water, which we talk about this week in our online ebook. We can talk about, there's 4 dimensions as we talked about. Atmosphere, it's a thin, tenuous blanket of air. One half lies below 5.6 kilometres and the other half extends beyond that. So this is what we understand to be. These are the facts of what we understand the atmosphere to be. The biosphere includes all life. This is what we mean by the biosphere, all life. It's concentrated near the surface in a zone that extends from the ocean floor upward for several kilometres into the atmosphere. So we can see that really most life exists within that first half of the atmosphere. Already we can see students start to make some connections. We are building what we call here our science understandings. So here's what we were talking about at this stage, how we can look through these different components and see these understandings grow. A view of the Earth, we can then talk about its geosphere. Now, Loxley's very quiet on this, which is a real shame, I think, because the geosphere is a really exciting area. Kids are very much into tectonic shift. They're into a whole range of rock formation, how to measure the weight of rocks, the mass of rocks, all of these different things for creating simple mathematics, STEM-type resolutions to this. But we can see it consists of 3 basic sets, and this is what we've just, this is what is agreed. These are teachable. So as teachers, if we think we know nothing about science, we can look at these 4 major spheres, and we can look at the agreed principles within them, and we know that we can begin to teach from these places. And that's what we've got to do in this course. We've really got to work out how are we going to bring learners to science. And we can do that by creating pathways. Here we've got 4 major spheres. The final one is the geosphere. And if we think about the Earth as its compositional differences, we've got the crust, which is the thin rocky outer layer. We've got the mantle, almost 3 kilometres thick, located below the crust, immediately below the crust, and the core is the innermost layer. Once we do that, we can then start to actually look at diagrams, and we can create some connections here. We can see the crust, the relationship to the upper mantle, and we see right down here to the inner and outer cores. And we can break that down even further. We can see the oceanic crust, the continental crust. We can see the difference between land masses and water masses. We see the lithosphere. We can see the asthenosphere. And of course, we've got the upper mantle here too, and within that particular. So what we're doing is we're building schema. We are creating science understanding. And this enables us to teach things such as plate tectonics. We can use GPS to determine location. Geocaching. I don't know whether anyone's heard of the term or anyone's engaged in any geocaching activities, but it's fabulous. As a teacher, you can go out into the schoolyard and you can locate any bunker, really, and you can put some information there or some some clues, a whole range of things you can put there, some information, and you can send students on a geocaching quest. And they can use their mobile phones, and basically they can use GPS to locate these little caches. They can go there, they can solve the clue, and then they can go to the next one using their GPS system. And all of these, activities build upon our basic knowledge of the geosphere. And we then move to maps and mapping, cartology, and topographic maps, and we move there into looking at surface features. So we're talking here about the Earth as a system. We've talked about the 4 different formations within that system: the atmosphere, the geosphere, biosphere. And we can define a system as a teacher. We can define a system as any group of interacting parts that form a complex whole. So this is systems theory. And closed systems are all self-contained. For instance, we've got a motor car. The engine of a motor vehicle is a good example of it being, well, really the cooling system, but even not the cooling system, because you have to add water and you also have to add fluid to that, cooling fluid. But basically any system that's closed, and a good example is an automobile motor or cooling system. Open systems allow both energy and matter to flow in and out of the system. And there we can look, for instance, the difference between man-made systems and natural systems, such as a river. So what we're doing here is looking at this one area, this area of earth science, and saying to ourselves, look, one of my biggest fears as a teacher is the fear of failure, of the fear of standing up there and looking like I don't know what I'm talking about, that, there's a kid in the class who's going to know more about this than me. Well, I'm telling you that's true. So what you need to do is stand up there with your teachable moments in mind. What is the structure? What are the 4 formulations? What is the system? And, is it a closed or an open system? If we're at this point, then all of a sudden as a teacher, we are going to know, we're not going to know answers, but we're going to know where to direct questions. And that's the key thing to being a teacher: thinking on your feet, having enough knowledge to be strategically negligent to the point where you're not retaining useless facts, but you're actually pushing students towards the facts that really matter. When we look at the earth sciences, we can talk about the Australian curriculum and the earth system science. The ACS tries to bring it to us as a dynamic body, and it's got many separate but interacting parts or spheres. And we know this. We look at the substrands. We've got the science understandings, we've got the science inquiry, and we've also got the science as human endeavour. And we can match this across each of the unit elaborations and the teaching elaborations. And we can see that the ACS is really trying to make this curriculum interact, bring these parts of the curriculum together. And each system studies the Earth as a system that is composed of numerous parts or subsystems. We know that. We talk about biology, Earth and space. Next term, we talk about chemical and physical systems. In Loxley this week, we talk about the sources of energy, the sun, and it drives external processes such as weather, its ocean circulation, its erosional processes. We also mentioned the Earth's interior. It drives internal processes, volcanoes, earthquakes, mountain building. And human endeavour, we also talk about humans as being a key part of this Earth system, in particular the increasing population and the stress that's putting through interdependence on our Earth as a system. So what we're looking at this week is really the same formula that we've looked at when we looked at biological sciences and when we looked at space sciences. It's not saying to you, become an expert. It's saying to you, become familiar with the framework. And as people move through that framework, know how to direct them. Okay, we know that we have sources of energy and we can break them down: the sun, the Earth's interior, and of course people and our fossil fuels and our alternate energies. So we can move on to look at people and the environment. And yes, we can look at the different structures and facts of the environment. There they are. But the environment is basically what surrounds and influences organisms. And this is the scientific definition we can bring to it. We know that our physical environment includes water, air, soil, and rock. And the term environmental is usually reserved for those aspects that focus on the relationships between people and the natural environment. Okay, so we know that there is, if you like, a social connotation to the term environment, environmental. And unfortunately, rather than environmental, we tend to think of conservation. And unfortunately, conservation seems to mean keeping things the same. Now, keeping things the same, or, maintaining the status quo, is really it's really anti-evolutionary. And so, as teachers, we really need to be careful about conservation and not mistaking environmentalism for conservation, because conservation about keeping things the same, I really think the horse has bolted. What science is doing and attempting to do is actually trying to encourage a shift towards environmentalism, where we're looking at how renewal processes and processes, areas that have been extensively farmed and over-farmed, how they're coming back to life, and they're coming back in a new form, not the form that used to be. So we're talking here about environmental versus conservational. Resources. This week we talk a lot about resources: water, soil, minerals and energy. And they're broken down by Loxley. Here we've got a really nice split: renewable and non-renewable. I think that most of us get that without too much ado. I think it's quite a reasonable thing to pursue, and quite a reasonable knowledge framework to understand. And of course, the rundown or the breakdown of non-renewable resources will create an energy crisis in the future. And of course, that's what's driving a lot of our science as a human endeavour. We're actually looking at how to create alternate sources of energy. We talked also this week in the ebook about the growth of the world population and the stress that that's creating on environmental problems. Now, this is a really good angle to bring students to, this whole notion of earth sciences. Here we've got a little diagram. We know that, human usage patterns here at the bottom of the chart can actually affect ozone layers. It can affect the atmosphere. It can affect the air quality. We know that pollution is a huge factor. And we can now also, through the process of science, help our students understand the impact of the upper atmosphere on the lower atmosphere, and how that is actually going to exacerbate environmental issues. We can also look at regional, local and global environmental issues, how what we do locally creates the regional environment and therefore contributes to the global outcomes. So we've got those connections running nicely through the ACS. People, over here we can see the current world population is 7.6 billion in 2018. As you can see, in 18 years it's grown 1.5 billion. So our growth is now, better health, better, increased wealth, democracy, the absence of any serious war or serious virus or illness. We're starting to see the Earth's population become quite sustained. And as a result of the increased population, we're starting to see these factors come in throughout the world. And we're starting to see the impact that's having on our natural environment, which of course we now know is not sustainable. And we've also got our natural hazards, which are a fascinating thing to do. Like last year we had Cyclone Debbie and its influence and impact on the Mackay region. Even though it predominantly came in as a low, it caused extreme devastation and had a huge impact on people and their environment. Strand 2, throughout this course, we've talked about scientific inquiry a lot. And we've raised the 5 E's model. And we know in the first E, we're all about the teacher. It's all about the teacher working out what students know. So the teacher then, at the end of the first E, is theoretically in a position where they can now, they've been the sage on the stage. They've actually mapped the learning in the classroom. They know what the misconceptions are. They know what the knowledge gaps are. They know what knowledge exists. They know what half knowledge exists. So they can then set about this correctional process of learning. And this is what we call pedagogy. So scientific inquiry really starts to kick in about the 4th E. Okay, we go through the explore and the explain stage. So we're exploring the knowledge in the room. Then we start to explain the science behind the knowledge so that the knowledge in the room can be aligned with scientific knowledge. And then at stage 4, we ask, well, how do we know this? Strand 2, what is scientific inquiry? So scientific, if we look at science as a discipline, it's only, the word science is only 120 years old, okay? But if we look at scientific discipline as a construct, we can sort of see 2 assumptions. It's consistent and it's predictable. And the goals of science are to discover patterns in nature and to use the knowledge to predict what impact nature will be exposed to as a result of human or other activity. An idea can become either an hypothesis or a theory. Now we're going back over what this entire course has been suggesting at each level, in each unit you've looked at, in each assessment task you've looked at. A hypothesis, of course, is tentative and untested. A theory is tested, confirmed and supported until it's disproven. Don't forget Karl Popper. Scientific method, we spent a whole week on this, thinking scientifically, gathering facts through observation, formulating hypotheses, testing hypotheses to formulate theories. So we're sending students out, in that fourth and fifth stage of the 5 E's, to basically go out there and evaluate, and extrapolate. So, we're really asking them to apply the scientific method to their frameworks. The inquiry process, which we talked about throughout the course, and even though we looked mostly at units in the 5 E's because that's what's taught in the Queensland curriculum, we also mentioned the Legos, the 4 C's, the POE, the very strong New Zealand model, problem-based learning. Some of you may be picking up on these in your digital cards. But the whole principle here is through the inquiry process. Science knowledge is gained through the following steps: collecting facts, developing an hypothesis, conducting experiments or making observations, re-examining the hypothesis and accepting, modifying or rejecting it. Science is about formulating theories. The students in their own worlds, child as a scientist, formulating theories that withstand examination and will be open to further examination. Okay? So these are the things that we've been talking about all term, and this, this final unit is really no different to that at all. So which science do we teach? Do we teach scientific facts? And when we look at that diagram, we can teach what a CFC is. We can teach what a HCFC is. We can teach about halons and methyl bromide. We can teach the impact of pesticides, and we know that that's huge at the moment. There's a raging debate going at the moment about the inclusion of DCT, I think it is, in crops, in genetically modified crops. That 15 years ago, this was used as a poison to kill them. Now it's actually used as a supplement within the crop itself. It's been genetically implanted in the crop so that the crop resists bugs and resists fungi and resists a whole lot of natural predators. So we can see that that science has done a lot of different stuff out there in the environment. And the problem with teaching about methyl bromide and pesticides is that it's going to contradict. It's going to come into contradiction when students start to explore genetic modification and a whole range of other issues. And so we have to be careful about teaching science as facts. And that's the whole principle of the ACS and the whole principle of really what this unit has been about. We can reduce things to facts. Facts 1, fact 2, fact 3. But that doesn't help us understand the impact of our action as individuals in a world which is interdependent. And this is really what the ACS is trying to do, bring the child back to a position of being its own scientist. Now, to some degree, the facts are going to contribute to that discussion. Science understandings are important, but they're not everything. Okay, and science understandings are going to evolve as the learning schema evolves, as the child goes through the curriculum, as the child's knowledge base expands and they're able to make those connections. Give examples of how scientists use classification systems and why. So we talked about classification also, and I may need to take off my highlighter here too. Okay, my apologies there. Examples of how scientists use classification systems. We can talk about science and we can look at the earth sciences. We can talk about sedimentary rocks, sediments, igneous rock, magma, metamorphic rock. We can talk about the relationships between them. Okay, what actually happens, where the diagram starts. And we can see here that sediments, deposition, burial, cremation, and we can go through all of the organic structures here in the forming of rocks. Igneous rocks melt to form magma. Okay, we see all of the heat and pressure, metamorphism create metamorphic rock. Okay, metamorphic rock in turn links back into sediments. And we have this whole settling of the world. We can talk about relationships. And then we can give the kids a task to begin to work out, okay, where things start. What is sedimentary rocks? What are sediments? What is metamorphic rock? How do these things come together? Why do they come together? We can ask if and then questions instead of teaching knowledge. The same thing here, we've got here something, space sciences. And the whole notion of white dwarfs, red giants, supergiants, obviously it's a description of the stars. Okay, and we can see something to do with temperature. Blue stars, white stars, yellow stars, red stars. Okay, temperature by colour. Colour and temperature are obviously clearly related. And luminosity relative to the sun. We can see that certain ones are brighter. So what we're doing here is talking about the organisation of our solar system according to how it appears. Its visual representations. And so these are all the things that we can look at when we start to teach about scientific inquiry. Okay, we can talk about how we are going to measure instruments. So when we start to look at the volume of an object such as a rock, we can look at length by width if the rock is structured as a rectangle. And we can add height into that, obviously, to get our dimensions. We can use scales, or we could use water to measure the volume. We can put water into a container, and then we can add the rock, and we can see how much the water rises. And that will give us a measure of the mass of the rock or the volume of the rock. Okay, if an object is heated, what happens to its mass and why? All these questions we can ask students. How do we measure volume? Okay, and we've got a couple of different examples here. Again, using water, we have a different example. So, if and then questions. We can teach science. We can teach science understandings, which are important, but then we need to add to them, of course, the means to finding out and testing why they're important and how they come together. A couple of questions for you guys. How does a scientist express relationships? Well, here's where science crosses with maths. We're getting a little bit STEMmy here. And last week we looked at toilet paper rolled out across an oval as a way of measuring stellar distances. Here we've got, for instance, a couple of different graphs. And this first graph represents what we call a direct relationship. There it is, it stopped. Our second one is an indirect relationship. Our third one is a predictable relationship. And our fourth one, I'm going to ask you. So, can you think of two variables which have a direct relationship? It may be related to the unit that you're currently teaching or the digital card you're looking at. Is it sunlight and a plant, perhaps? Is it population and pollution? Is it distance from the sun? What two variables would result in a direct relationship? Because again, this is an excellent way for you to actually start to structure inquiry. Is just to simply have two variables that we've just done in the previous slide, and beside them a graph or an illustration. And again, getting students to work out what that actual graph is about, what it's telling them. An indirect relationship. So the more you have of something, the less you have of something else. The more hours of sunshine, okay, the less ice, okay. Predictable, okay, the seasons of the moon. We know that can be graphed. Is that a predictable graph? And what about this one? Something that's a flat line. What does that suggest about scientific relationships? If we have one of these, we've still got the same number. If this is 10, it's a flat line. So it's probably signifying a lack of relationship or a minimal or a constant relationship. So again, posing to you, we may not know a lot about science, but we may know a little bit about mathematics and graphical representation, mathematical languages. We can present science to our students in a whole range of ways, boosting a whole variety of literacies. Some examples. Here's a good one up here. Relative humidity versus air temperature. And we can see that, for instance, it's a predictable curve. Another one down here, we can see average rate of erosion, okay, and the relief in metres. In other words, how much is lost. So again, what do you think? Population versus pollution? Okay, probably going to be a direct relationship. Phases of the moon, probably predictable. Sunspots, Probably like this one here, I would imagine. Are they? Time versus the number of planets. Tides, probably going to be predictable. Density versus weight, probably going to be predictable. There'll be relationships in there. So we're looking here again at trying to point to different ways to present science, different formats that you can bring people into the scientific frame. And the third one I want to talk about is human endeavour. And here we go right back to the start of the course with, the poet John O'Donoghue. And he makes this beautiful quote when he's asked where he comes from and whether he thought it, the interviewer said, do you think it makes a difference where you come from? And he said, well, I think it makes a huge difference. When you wake in the morning and come out of your house, whether you believe you're walking into a dead geographical location, which is used just to get to a destination, or whether you're out emerging into a landscape that is just as much, if not more, alive as you, but in a totally different form. And if you go towards it with an open heart and a real watchful reverence, that you'll be absolutely amazed at what it will reveal to you. Now, it's a really interesting perspective on earth sciences, and it's often accredited to the First Nations people. Here it's considered to be an Indigenous perspective in Australia, but yet many of us come from a Celtic heritage and a heritage from Northern Europe. And again, prior to the rational age, prior to Industrial Revolution, this was a dominant paradigm in our thinking. We used to believe that we were connected to our lands. It goes right back to Celtic times. Somewhere through the industrial processes and the industrial mechanisms, we've actually managed to separate ourselves from our land and from our origins and connections to it. And we refer to this industrial technical complex. It's swept the Western world, and everything now in our world, our lands, our oceans, our space, our people, our environments, have all become commodified. They're resources that exist in order to satisfy our profit motive. And yet, we know that it could be quite different. And again, human endeavour, the shift towards sustainability, that connection that we've been trying to point to right throughout this unit of study. On the Moodle activities this week, there's quite a range of them, and they're all geared towards getting you to think about your digital cards. So we're trying to stimulate teaching ideas. And a little exercise here in species mapping where we did the food chain activity, sending the kids out into the yard, just with a simple one-pager, getting them in groups and getting them to chart all of the different species they can see in the yard. And then to come home, back to the classroom, and then engage in some classification, consumer, predator, okay? Get them to do some of that basic work. Really, really good hands-on activity. And as a digital card, that could work very well at home. Get them to chart the wildlife they see in their house, right from the very minimal type of animal, right through to the larger. Get them to chart them for a week. Get them to produce a graph. Get them to post the graph. If you're using a wiki, get them to post it in wiki or get them to blog their results. Do a Google Doc where the student can create one document, or a class group from one part of the town can create a document and they can share their results. There's a whole range of ways of doing it. The food chain activity. The food web activity was another one. Again, you can see it, illustrated over here. 10 or 12 students, a piece of string strung between them. And then you as a teacher, this is a teacher's fantasy, you legitimately get to kill one student. They have to drop their string. And then the rest of the network, if you like, or the cluster or the web, they have 5 to 10 seconds to make the string tight again. And you can see that the more species or the more students that drop out of that food web, the harder it is for that web to recover. And this is a really, really good activity, for teaching kids the principles. And we talked about glacier-eustatic recoil this week also, sea level rises. And we know that, it's much more complicated than some of the global science actually tries to tell us it is. Seas don't rise because glaciers are melting. Okay, there's a whole range of factors that work here. At Tuvalu in Venice, if you haven't been to Venice, do go soon. Last time I was there, for half the day it was underwater. So if Venice is slowly sinking, or is it the water horizon? We're not entirely sure. The Nile, the Indus and the Ganges rivers, what it's doing to low-lying fields and rice areas and unfortunately huge food catchment areas too, is having a huge consequence for our food futures. Energy and sources of energy was something was covered in Loxley this week, was covered quite well. Global warming, I pointed you to a site in Western Australia where it's got the most up-to-date information on what is happening in the global warming field, where the science has taken us. And again, it would be a great activity. They're all online. And it was, it was put up there for you to perhaps even use or modify or include in your digital card. And there's also a wonderful deforestation simulation on this week's activities too. We talk about clean energy. We look at some resources there, some videos about the use of puppets in the early years. And of course, the final video for the week looks at the conversation, which is an academic podcast, videocast, which looks at a whole range of important social issues. And the conversation that I featured on this week looks at changes to school science education. So, and brings in some of the points that we've been making right throughout this 11-week program, that some of the directions the curriculum needs to go into. So the Moodle activities this week should provide you with plenty of resources to get in and to be doing constructive, edgy, engaging, relevant digital cards. I'm going to pause now and throw over to you, and because maybe some of you will bring up some of the points raised in these forum items. Are there any questions people may have?
Colin?
Yes, fire away.
I did send through on the forum a question because I have based my primary unit on a year 4, but I see in the criteria sheet it's talking about prep to year 3. So I just needed clarity on that. Because in the cover sheet to the assessment task 2, it states prep to year 6.
Yes, indeed. Now, what I'll do is I'll just bring up my response to that. And there it is there. You're probably overthinking it at this stage. I mean, as I say there, we can look at legal reasoning to explore this, and okay, we go out and we come in and take a helicopter view. But what we're saying is that, there's a literal rule that what you see written there in a rubric is what needs to be done. That's true to a degree. What's there in the rubric is to guide you towards a solution. So what we're going to do is talk here about the golden rule. And the golden rule is the intention of what those instructions meant. So in other words, what we wanted you to do is realise that the curriculum has several ends to it, a top, a tail, and a huge middle. What this task wants you to do is demonstrate skills at 2 of those 3 levels. Now, if you say, I'm going to do it at level 4 instead of level 3, fantastic. Just tell us why. Okay, that's all it says here. You clearly have your reasons, so just include why you've used year 4. It may be pedagogical, it may be because that's where the curriculum pits, that's where it sits, and that's what the teachable moment is at that stage. Fantastic. Or it just may be that you thought this would be a really good illustration of how a digital card could add value to teaching, okay, by pitching it at a year 4 level in this unit. That's a valid reason too. The only thing is you're going to stray from what's written on the rubric. Just tell us what you're doing and why. The rubric was there to steer your thinking, not to narrow it down, Loretta. Does that help?
Yes, it does. That's fine. Thank you, Colin.
Good.
Yeah, because what I had is I had a topic in mind and I had a year level in mind, so I've structured it to that. But it is completely different to my early childhood card. It's much more advanced, and it's set for a year 4 student.
And you would expect it to be. So, I mean, that's pedagogically relevant. And
yes.
Obviously your TPAC would vary in there too. It may be technologically more challenging for that learner group as well.
Yes.
So there'd be a correlation there too. No, well done. I mean, that response is up there. And so just have a look at it. But, yeah. And Loretta and Kay are also snipping and snagging, which is a great thing. If you're not aware of that, Loretta actually shares some software that she's been using for capturing screenshots This was a big question 2 weeks ago. How do I get a digital image of my Weebly website? And Loretta shares some really good ideas with Kay there on snipping and snagging using a different piece of software. Maybe you'd like to talk to that, Loretta.
Yeah, it's Snagit is a similar to snipping, but snipping I find is quick and easy because I have it on the top of my browser. Snagit as well, but it has a bit more technical know-how in terms of how you actually snag the page and then you scroll down on your actual main web page. But if you just Google Snagit, I think there's a small fee that you pay, but it's definitely worth using.
Right, thank you for that. It's good to know. It's not something I've used either, so I've learned something as well. So it's great. Caitlin is considering play-based learning for Year 3 pedagogy, and she's wondering, is she on safe ground? Absolutely. You can use, I use play-based learning with corporate executives, and they go crazy. Let me tell you, when you get them to build a robot and compete using their robot against the marketing team, the execs go nuts. Play-based learning. And as I say to Caitlin in the post, you can walk around, you never see animals sitting down with whiteboards and blackboards and bits of paper and textbooks. It's all the learning is done through play. So if you want to use learning to teach Year 3 pedagogy, play-based learning, it's a fantastic strategy. I encourage it. And there's a whole lot of curriculum out there doing it. So don't think you're on your own, Caitlin. Go for it. Kate and Carly are running into permission issues when they try to use a game as one of their card assets. So just check that, because if you're putting in a digital card and it's got permission issues, it may mean that you've got access to it to use for your own purposes because you've perhaps registered. But if a marker uses your card or worse still, a student tries to use your card and tries to go to this game to complete the set task and can't do it, your whole learning sequence is at jeopardy. And so if a marker also tries to get to this simulation that you've recommended as a key learning asset or artifact in your learning sequence, and they can't get in because it's got permission issues, then chances are that's not going to help your result. So please check those things out. Even if you're using a Weebly, make sure the Weebly's not locked down so that a marker can actually access it, because they will look at one of the big questions, two which I had this week, I'll raise them. They'll look at the conversion from your card to how it connects to your Weebly page and the consistency and how that learning tool, the digital printout, comes to life as a website. So that's really, really good. Digital skills to be teaching that way, good pedagogy. And so the markers will want to go and look at your resources. You've taken a lot of time and effort to build them. So the markers are going to go and enjoy that journey. So make sure your links are not locked down due to permissions, okay, or passwords. Noelle had a question about teacher elaborations. Now, I can't exactly remember what that question was, but it had something to do, I think, with do you include your teacher elaborations and how much information do you put in them? The teacher elaborations are really a teacher card. So you don't want to be writing a thesis in them. You will have your digital card for the learner, and then your teacher card will be there for the teacher for instruction. And it may include some notes on differentiation. It may include some notes on technical requirements. And it just may include the lesson sequence and may list the key pedagogies. But you don't need a lot of information on your teacher elaborations because all of that should be explicit from part A of your assignment. You've already done that. Part B should just be a card for teacher elaborations, which is a visual representation of what you're stated in part A. Loretta again provides some great links to resources, and I really enjoyed having a look at those. Don't forget the ICT one, the first link she provides, you need to register to get access to. But it's really well worth registering. It's free, so make sure you do. Carly had a question on how to structure the early years learning framework task card, because it's years 0 to 5 and they're very different in their learner focus. Pick 1 year, okay, or pick 2 years, pick an age group. And just specify that this is the level that you would be pitching towards. Take control. You're able to do that. Again, to go back to the very first question, we're the task here is creating there's 3 distinct chapters of learning here, the early years, the primary, and the upper primary, early secondary. Pick 2 of those chapters and narrow it down if you need to, if you want to. It could be year 4, it could be age 4. Tell us why you're doing that, okay, because it's relevant to your curriculum and your teaching. Fantastic. And then just do it. Okay, take confidence, take control. The more you are in control of this particular task, the better it's going to go for you. Okay, and I had another question too earlier in the week, an email one, which I haven't posted here, and it was from another one of the teaching team who had a student who wants simply to do Word digital cards. Now, that's fine. You can do. There's no requirement on you to have to build a Weebly, but anyone who's tried to teach, and I do emphasise the but, if you've tried to teach in an online environment, online environment, and you have not curated your resources and secured them, there is a thing called link rot. There are things called dead links, and it's really important to know that if you're going to use a resource, that it's as reliable as the electricity and the water. And so the best way to do that is to curate it into your own Weebly and have it, running and having the links constantly checked and updated. A Word document becomes a snapshot in time, and it does increase the likelihood of link rot and dead links. And also visually and aesthetically, it's a little bit more challenging, though 2 weeks ago we did give you some strategies, PowerPoint. You can do really colourful Word documents. It's not a problem. You can include text boxes and set them out really nicely. We're not saying don't do Word. We're just saying, here is an opportunity to create a learning environment, which includes a digital component, your Weebly, and also your link to that, which is your pipeline, which would be a Word document or a digital card of some other format. So the Word documents do have much less, if you like, applicability, much less functionality than the Weeblies, and also much less control over your resources. And that's why one of the reasons why we do push you towards a Weebly, but we don't exclude the use of Word documents at all. And another point too I want to make, please, feedback. We would love to have your feedback. It's there available at the moment. I think we've got 8 people out of 161. That's not very many. Okay, so we it's about 5%. We need more than that. And plus, we also want to know what we can do with this course to boost it, to make it more suitable for the next generation of learners. We also want to know, is our feedback getting back to you in a timely way? Is the information clear? Are we being clear about the assessment? Anything that you can add to us that might help us deliver this course better in the future, or deliver it differently, do less of some things, do more of other things. You're almost teachers now. We really do value and respect your input, and we would use it to improve our product. So if you can, please, I open that invitation to you again and encourage you to have something to say about your experience in this program. It's all anonymous, so I never know who says what, but I have a huge regard and trust for you, and know that what you'd say would be well intended and would be designed for positive, constructive reasons. And so I'd warmly take it on board. So are there any specific questions from the group for the rest of the night for anything else? Any other questions or areas? You'll get another chance next week. There is one more Zoom session. And next week's Zoom session, there will be virtually minimal content, and it will be a Q&A. And I'll be here to answer any questions you have before submission, which would be the following night, the night after the final Zoom session. Oh, no, actually the week after. Yes, so it's actually due May 31st. So, so it'd be the night after, actually. So my apologies. I've been away for 5 days, so I'm catching up slowly with my head and with my dates, and also my PowerPoints. So, so please bear in mind that will be a fairly open session, and I'll be happy to answer any questions that you bring to the fore. But again, point out to you, please, your digital card. Here we've got 2 variations, one for the teacher, one for the student. And you can see that this one really represents the pedagogical intent. The learner group is targeted, the resources are clearly and excitingly presented. The learning sequence is explicit. There is applied pedagogy here. To submit a Word document that looked like this, you're missing the opportunity to embed your pedagogy. You're missing it. And yet, therefore, you're missing out, I would think, on higher order outcomes for yourself. We expect to see your full TPAC. So we expect to see some technological skills in operation. Our fourth year students at the moment are going through their huge GTPA completions, which is the 8,000 word document they have to complete on how they meet graduate standards prior to their employment as a teacher. Now, you've got that coming in year 4, but the best way to do that is to do things like digital cards, because you can demonstrate your digital competencies. This digital card, believe it or not, would tick all of the graduate competencies for that particular task. And again, one of the cards is functional, one is clearly for learners, but they need to be a dialogue. They should be presented together. The teacher elaborations should explain what's happening in the digital card. Are there any questions or grey areas there?
All good here, Colin.
Lovely, thank you very much. Anyone else? Any questions? Just because it's good for one person, it may not be good for you. Now is a really good time. All right, judging by the silence, I will assume...
Sorry, Colin, one question.
Yes, fire away.
The digital card, do we need to embed that as well into our Weebly?
No, it simply will be one page of the Word document you submit. Part A obviously will be typed as a Word document. Part B, you'll probably have a screenshot of your digital page and your teacher elaboration for each of your 2 cards. But you do not need to embed an image of your digital card in your Weebly. There will be a live link that comes from your digital card that your marker will be able to click on as they're marking your work, and it will take them to your Weebly where they'll be able to enjoy the integrity of the resources you've put there.
Sorry, then in the Word document with our Part A, so we can add appendices of the 2 digital cards and the 2 teacher elaborations.
I would just make Part A my written response.
Okay.
And Part B, I would make my 2 digital cards and my teacher elaborations.
Okay, super. Thanks, Colin.
Make it that explicit. And that way your marker gets in and they see everyone's Part A. Fantastic. Let's see your Part B now. Let's see your digital card. Okay, how's a teacher going to use that? Wow, this hangs together really well.
I'm with you. Okay, super.
Good.
Thank you.
Are there any other questions? All right, please, if there are, please commit them to email, commit them to forums, and let's go through this final stage of this program, and hopefully get into next week. We can start sharing some of these resources, because certainly some of the work I'm seeing come through as draft form is really very exciting. I think there's some schools out there and some kids who are going to be in for some wonderful science experience and experiments and processes, and so I just take my hat off to some of the work I'm seeing. So please keep those questions coming, keep the dialogue alive, and I just encourage you to ask, no matter how silly you think the question may be. On that note, I'll say good night.
Thanks, Colin.
Thank you.
Thanks, everyone.
Bye.